We'll try a few questions on this worksheet together. Yeah, and today we will have to fill out this table. Okay, there's a new worksheet distributing to you by your fellow classmates. Okay, and we will be filling out this worksheet. Okay, so let's start. We only have a single lesson today. So, first of all, we need to discuss like some properties of. Can I have your attention? Okay, yeah, so turn to a new page on the first before we fill out this thing. Yes, thank you. Make sure everybody has a copy of this table. Okay, so we're not start. So starting with covalent, we look at properties of. Right, so get the worksheet. Don't work on stuff from us, something like that. You're not here to learn the business. Okay? Right, so starting with properties of covalent substance. So we have two types of covalent substances, as you remember. So they are simple molecular substances. Like that. There are two main types. Right. Okay, two types. Okay, so we have simple molecular substances. Try to come to class on time. So simple molecular substances, aka also known as simple molecules. So when you see the word simple molecules in your hand, it means simple molecular substance. This is one type of covalent molecular substance. The other three, okay, that you see on the other side, okay, is the giant covalent structures, okay, the giant covalent structures. So under simple molecular substances, I want you to put down a bunch of. So I want you to put down a bunch of examples, including CO2, CH4, C60. Okay, so all these examples have one thing in common. They have a fixed countable number of atoms. Then on the opposite side, okay, you're not filling this in on the worksheet first, but you may use the space on the back, okay, to jot this down if you like. So, but I still recommend you put it on the I'm just worried that you might lose this page. So, giant covalent structures can be diamond, graphite, silicon, or silicon dioxide. Okay, so this may look like a very long list, but only these four substances you should know. They have giant covalent structures. So almost all other known natural elements and compounds, they are put into the left-hand side category. Okay, right. Keep quiet. Okay, yeah, keep quiet. Okay, so when you're talking, the other students they cannot listen. Okay, right. So we have simple molecular substances and giant covalent structures. Now we look at their properties. Okay, starting with the melting and boiling point. So can you put down melting and boiling point? Right. When we look at simple molecules, what do we call the interaction between the atoms and within the atom? Do you remember? Within the molecules, there are strong covalent bonds. So let's draw CO2 here. Okay, I'll just use CO2 here as an example. When you want to melt or boil like a CO2, only what do you need to break? Only the weak intermolecular or weak intermolecular bonds. So can you put that? When you melt or boil simple molecular substances, you only need to break, okay, the weak intermolecular forces needs to be broken. Okay, so need to be broken. You see the covalent bonds, they remain intact. So this is why they are still here. Okay, so you see the orange ones. Okay, those are the covalent bonds. They're still there. They're not broken when you melt it. So this is is the solid state, and this is in the liquid state, right? What about over here on the opposite side? Can you jump in count? Can you hear me? So on the opposite side, we have the giant covalent structures. I hope you still remember how to draw diamond. How many other carbon atoms is each carbon bonded to the
5. Wait, no, 4.
4. Yes. What in graphite? 3. Yes, 3. Okay. So can you split this off into two parts under giant covalent structure? Because we often compare two forms of two forms of carbon. One is diamond. The other is graphite. So while both of these they are classified as giant covalent structure, as you'll discover, they have some slight difference. Okay, like these two forms of carbon. So I want to split this table off. Okay, so there should be 3 columns on your notebook. This is the first column. This is the second column, and here is the third column. So there should be 3 big columns in here. And for the middle section here, we'll just put down some physical properties. So these things I'm writing in blue, they are known as physical properties. Okay, you might remember learning this in Form 3 as early as in Form 3. Physical properties are properties that you can study without forming new substance. You know when you melt something, yeah, granted, I guess a liquid, okay, after you melt a solid. But the particles that make up the liquid are still the same particles that make up the solid, right? Just that the spacing are different, right? So can you put diamond here? Just draw a small section of it. And ask you to draw a very large structure of it. Just draw maybe three tetrahedron here, or tetrahedra. So, this is what we call a tetrahedron. A tetrahedron has all 6 sides equal. Okay, so this edge here has the same length as all the other edges. So we call this a tetrahedron. So diamond is essentially a bunch of carbon tetrahedra connected, okay? So you might want to draw it like this. Yeah, so drawing it up to this point would be good enough. Okay, so you have C, C. Can you see that I'm just duplicating this tetrahedron over and over? I copy it, I paste it here, paste it here, paste it here. Then you can treat carbon as a bunch of connected tetrahedra. Okay? So write down this shape. You will learn this again in Form 5. Tetrahedron. It's a shape with 6 edges, okay, with 6 edges being equal in length, okay? So with 6 edges being equal in length. So that's diamond. Yeah, with graphite, okay, we have carbon connected to 3 other carbons. So this we discussed, okay? So we're not going through this in detail again. So you have, right, like these carbons connected. And graphite, unlike diamond, okay, it's different from diamond in that it has a sheet-like structure, layered structure. Diamond does not have a layered structure. Diamond consists of a single molecule. That's it. So this whole thing in here is continuous. It's never broken in the middle. So this is a single. So diamond has a single large molecule. So graphite is different. Each of these molecules are still very, very large. Okay, so this is a large graphite molecule. But unlike diamond, there are many of these large graphite molecules that interact by weak intermolecular forces. So you can say in this regard, it is quite similar to, can you see that the graphite is quite similar to the simple molecular substance? It is more similar to simple molecular substance than it is to diamond, if you ask me. Because do you see any yellow thing in diamond? No. No intermolecular force in diamond. But you see the yellow weak intermolecular force. So weak intermolecular force between layers. Yeah, and you will have these strong covalent bonds between layers. So these are strong covalent bonds. But then, when we melt diamond, what do we need to do? We will need to use a lot of heat. Okay, because to melt it, there's only one way, right? Is to chop these strong bonds. Okay, cleave these strong bonds, and it will take a lot of energy. So can you put that when you melt diamond, you have no choice but how much force is needed to separate the layers, well then you will say only the weak intermolecular force needs to be broken. But if I'm talking about turning both of these into a bunch of disconnected carbons, let's say I think I will call these carbons, well then you must break the strong covalent bonds. So this is why both of them, despite looking very different, they will have high melting and boiling point. So with that being said, you can now fill on this page. So I wanted to split up giant covalent structure, take out a ruler, split this up into two columns for the giant covalent structure. I'm going to do okay, so you have to do that. Split just the giant covalent structure column into two halves. So equal halves with your using your ruler. Okay, and we will fill that in. So let me tell you what you need to put in there. Right. Okay, so I'll just put it in here. So for giant covalent structure, you see melting point there. So melting point, and then you have so you have giant ionic, giant simple covalent or simple molecular substance, and then you have giant covalent. So only for giant covalent do you need to have it split out into two, okay? And then you can write down diamond and graphite in no particular order. And you can put graphite first if you like. Just make sure you know one is diamond, one is graphite. And then we will fill in the melting point part. So the melting point of both of these substances are high. Okay, high. Because strong covalent bonds need to be broken right now. So strong covalent bonds are broken. And it is because they are strong that it takes a large amount of energy to break them. Yeah, so that's what you should put for graphite and diamond. Now, we turn to the Ionic trouble. Okay, yeah, so if you make a mistake, like you did an extra copy, I have some more to do. So, okay, after this is done, okay, you can also fill out the rest of these cells. So we haven't discussed giant metallic, so we will leave giant metallic till the very end. But can you put down for simple molecular? What can you say about the melting and boiling point? Is it high or low?
Low.
Low, because only which type of interaction needs to be broken?
Weak intermolecular.
Weak intermolecular force. So write this down. Okay. So only I will try to keep the color consistent. Okay. So if I use yellow for intermolecular force, I'll try to using that. So only weak. Underline the word weak. Because you only need to break weak forces, very little heat is needed. So low melting point. This will definitely appear in your Form 4 exam. Okay, yeah, so because I already made the figure. So only weak intermolecular forces are broken. So no wonder they have low melting point. Now, to check if you actually have done revision, can you tell me what about giant ionic substances? Do giant ionic substances have high or low melting point, and why? High. Why? Because what is the type of interaction found in giant ionic structure?
Strong covalent bond.
Strong ionic bond. Okay, remember when you say ionic structure, we mean ionic bond. Okay, so we'll put down the word high again, but don't say there is strong covalent bond. We say there is strong ionic bonds have to be broken. Okay, so have to be broken. And if you still have space in here, you can draw out like a bunch of ions, and you can write down where are the ionic bonds found. Well, they are found between ions of opposite charges. Okay, so you have them here. So these are the strong ionic bonds here, and like everywhere. Okay, like chains. Remember, like these are what chain up these ions together. And when you talk about weak intermolecular force, yeah, so draw two molecules here. Let's say you have, this is H2. This is another H2 in here. We are talking about the breaking of these intermolecular forces. So these are weak, so it doesn't take much force. Yeah, and for diamond and graphite, there's too little space to write in here. Okay, so I will we will just draw it on a separate page like we did. We will look at giant metallic the last. Okay, don't worry. Let's not worry about that column for now. So this is what you should put down in the melting point or boiling point column on your worksheet right now. Okay, melting point. And you see I already wrote this down for you. This depends on the strength of attraction that you need to break. If they are strong bonds, or high melting point. If they are weak bonds, low melting point. Okay, so strength of attraction, you don't have to copy this in green. I already wrote it down for you, see, in the first column. So you have to break. And then we look at the electrical conductivity. Okay, we already discussed this for ionic structures. So electrical conductivity depends on the presence of two particles. So it depends on the presence of what? Mobile ions and the localized sea of electron. Yeah, so put it back. So it depends on number one, mobile. You just have to underline it because I already wrote it down for you. Okay, mobile ions, and number two, the localized sea of electron. So mobile ions, you can now add to your worksheet. Okay, it can only be found in ionic compounds. Okay, so found in ionic compounds. You cannot find ions in covalent compounds. Okay, generally. And the localized sea of electron can be found in all metals and one non-metal. What is that one non-metal with the localized sea of electron? Graphite, yeah, in your pencil case right now. So found in all metals and one non-metal. Okay, and this non-metal is graphite. Okay, not diamond though. I know diamond is also carbon, but not all forms of carbons are created equal. Graphite is an unusual type of non-metal. So of course we know all metals conduct electricity. That's why electrical circuit they are like made from copper, right? Copper wire. You see a lot of copper in electronic devices. Maybe in a computer, in all kinds of electronic appliances. So now let's fill out this table. Can ionic compounds conduct electricity?
Yes.
Well, the answer is it depends on the states. Which states? We already mentioned this on one of the papers, like some molten and aqueous, but not in solid. Okay? Does anyone remember? If you don't remember, let me refresh your memory. This is where we talk about it. We said in the solid state, this is in the solid state, the ions, they are all held in positions. They cannot move. Okay, as there are no mobile ions due to the strong ionic bonds holding the ions together. They are strong bonds holding them in place. But I said you can do two things to break those ionic bonds. Number one is to heat it very strongly, or to add water. Okay, turning them into molten and aqueous state. You must remember these three words: aqueous, molten, and solid. It does not conduct in solid state, but it conducts in molten or aqueous state. Okay, so non-conductor, or you can just write insulator in solid state. Conductor in molten and aqueous state. Okay, so add this to your worksheet right now. So right now it depends. Okay, and you can say in solid state, in molten state, and in aqueous state. So draw it like this, sorry. So aqueous, okay, solid and molten. So in solid state, just draw a bunch of ions connected. They are all chained up by strong ionic bonds. Don't use the wrong term. Okay, so there's strong ionic bonds. The ionic bonds hold the ions in place. They can't move. So therefore, we say there's no mobile ion. So no mobile ions. Therefore, non-conductor or insulator, you can just say. But then we can do two things. Number one, we can add water. So we can add water on the right, or we can add a lot of heat to get to molten state and aqueous state. Write down the state symbol. You will see state symbol very, very soon when we balance diffusion. Bracket S means solid. Bracket L means molten. And this is not E, this is L. I just like to write L this way. You can just write L this way. Okay, but this is how I like to write L. This way. Okay. Yeah, so bracket L. And then finally we have D2. So what do you find in these two states? So on the left, yeah, you will have a bunch of mobile ions, but this has to be heated. So you need to keep heating it to keep them in this state. And on the right, you will also have mobile ions, but you don't have to heat it. You only have to add water, and then they will remain in that state. Okay, so you have water in here. So what's in common, okay, for both of these is that they both have mobile ions. So I have mobile ions. Okay, and so they are conductor. So this is why the answer is it depends. It depends. It's not a straightforward yes or no. What about simple molecular substances? Do you see any ions when you look at this diagram here?
Yes.
Ions.
No.
No, what do you call this? More molecule. Yes. Okay. So maybe you can also add this in here. So these basic components, we call them ions. This basic component, we call it molecule. Molecule is not an ion, you know. So right now it is not an ion. So okay, so you see molecule is not an ion. So therefore they are not conductive, okay, usually. So therefore you can say electrical conductivity, no, okay. So they are non-conductor, or just write non-conductor. So non-conductor because they lack both delocalized C of electrons and mobile ions. They lack both. So they can't be conductor. Okay? We're working on it. We're filling on this worksheet. It's blank. So next up we have diamond and graphite. Which of these two forms of carbon is a conductor?
Graphite.
Graphite. Okay, so can you put down conductor? Make sure you read the correct order. It's graphite, they will be conductor. For diamond, we will still put insulator or non-conductor. Okay, so non-conductor. So for graphite is a conductor. Why does graphite conduct electricity? Because it has, is it mobile ion or delocalized C of electron? Does graphite have delocalized C of electron or ions? Does both? It has delocalized C of electron. Remember? Yes. I know it. I will go back. Okay, so let me refer to this first. In graphite, each carbon is forming 3 bonds, using up 3 of its 4 outermost share electrons. That means 1 electron can like a wander off, right? Okay, that's a delocalized C of electron. So therefore, it is a conductor thanks to the delocalized C of electron. Okay, so let's go back and fill this in. So non-conductor because 4 of 4 electrons are used up. So 4 of 4 electrons are used up on each carbon. So therefore, no delocalized C of electron, making it a non-conductor. But then we have on the right, graphite. We are doing it in the same pace. Well, then you should have copied earlier. You can refer to the video later. We are working on this worksheet together. How come all the others can copy and you cannot? So don't worry, you can refer to the video later. Okay. So you have 3 of 4 electrons being used up on each carbon. So therefore, there is 1 delocalized electron for each carbon. Okay, and all these electrons, if you give up $1, your friend gives up $1, well, eventually that makes a lot, okay, of money, right? So if every person in Hong Kong gives up $1, there will be more than 7 billion. Okay. So you have one delocalized C of electron per carbon. So this will make for a very large delocalized C of electron. So it is a conductor. So make sure everything makes sense to you. Okay, it should naturally flow, the logic. Yeah, like I said, we'll deal with the giant metallic structure the last. Okay, but everyone should be at the second rule now, electrical conductivity. Then there's hardness or strength. So hardness and strength, you see, depends on what happens when you deform the structure. So now we are at the third row. So hardness or strength. Okay. So for this part, I wanted to draw like a before and after diagram. Okay, so this is what you see before you deform a structure, before you deform the giant island structure. And then on the side, I wanted to draw what happens after you deform it. So to deform something means to shift the layers around. Okay, so you are deforming it. So when you deform the structure, can you tell me what you see? What used to be attraction will then become repulsion. Okay, so you can put down a key here. Use some color to help you. Yeah, if it's all black and white, you do not want to read it. Okay, but you can print this page out, the notes I'm writing right now if you want to use that. So we'll just put down attraction. Yeah, these orange lines, they are attractions called ionic bonds. And then on the side, what like I said earlier, what used to be attraction will then become repulsion because light charges repel. So you see these arrows means repulsion. Write down why. Because light charges repel. Yeah, and don't forget to put down before and after here. Yeah, before and after what? Before and after you deform the structure. Okay, so this is deformation. In the middle, you change the shape. When you push something really hard, you deform it. So when you push the giant ionic structure really hard and create a fault, this is what we call fault line. Earthquake occurs because of a fault line, like underground. Okay, but I'm not putting that word down to confuse you. Just know that when you push on something really hard, you will, damage the structure. So it will create a separate layer. And when you slide these layers apart, it went from attraction to repulsion. So the word we use to describe ionic compound, you still have to put this out, is that they are hard but brittle. Brittle means they break easily. Okay? They break easily because the attraction will become repulsion as you deform it. Okay? So you don't want to make something very useful out of ionic compound because they will just break easily. Okay. Now for molecules, okay, usually we don't use the word hard to describe them. Okay? So you can write down because they are usually liquids. You can say because of the first property, that they have low melting and boiling point. That they don't usually exist as a solid. Can you use the word hard to describe liquid? No, you can't use the word hard to describe gas either. Okay? So therefore, because they usually have low melting and boiling point, we say therefore they usually exist as number one, gas, volatile liquid. You should learn the meaning of the term volatile if you don't know what this word means already. Volatile means it becomes a gas easily. Alcohol is a volatile liquid. When you spray alcohol on your hand, a few seconds later, it's gone. This is what volatile means. So it becomes a gas easily. Okay. Water is not as volatile. Well, it can still evaporate, but it doesn't evaporate as quickly as alcohol, right? So you can write down alcohol. Okay? And rarely a solid. So they are rarely a solid. Yeah, but I wouldn't use the word hard to describe a solid. Okay, so therefore you can say the term hard does not apply to them. Okay, so the word hard does not apply to them. And right, what about for diamond? experiment that I asked you to do is to use your pencil to sketch, yeah, on the piece of paper, and then try to feel it. Okay, try to touch, yeah, the smoother surface. You will feel the smoother surface when you put your finger, when you run your finger on the graphite. So that will feel that soft and slippery. Okay, and next year you bring this paper back, okay, and I will collect your homework on this lesson. Okay, next lesson. Next lesson we have the next lesson.
What's the homework?
Oh, the homework is that worksheets. Okay, yeah, I have homework.
Oh, sir, I wrote the notes on my.
Oh, not this one, not this one. It's this one.
Oh.
Right, yeah, so I'll collect it next week. Yes. Oh, if you need an extra copy, you can come with me to the staff. Okay. I'll give you. But yeah, please refer to the notes. After we are done with this topic, we will have a test. Okay, because this is the last part of this section. Okay, the next topic will have a test. Okay, so we will have a test in 1 or 2 weeks.
Really easy.